Good morning, everyone, and thanks for watching. I'm Terje Rølvåg, the administrator of this project proposal titled Digital Twins for Structural Health Monitoring and Predictive Maintenance. This is a multidisciplinary initiative from professors at the NTNU departments, MTP, IMT, and KT from the Faculty of Engineering and the Department of Mathematical Sciences from the Faculty Information Technology and Electric Engineering. And the purpose of this video is to demonstrate the benchmarks which have initiated the research questions that we want to address in the PhDs. There are basically two types of digital twins. You got digital twins for processes and digital twins for products. And in this project, we want to study digital twins for structural integrity monitoring. That means we have a physical device like this, and this one is instrumented with an accelerometer, and it's integrated twice in order to capture the displacements here. We could also instrument it with strain gauges that could, by using inverse methods, estimate the applied load. So we either have to estimate the applied load or the applied displacements. And those are transferred to the digital twin and applied here as loads to this virtual model or this FEM model. And then this FEM model can be used in order to capture the stress distribution for predictive maintenance and fatigue analysis, for example. And you can also use it to capture all other failure modes. So let's demonstrate here. Here we apply the displacement, and you can see it's being transferred to the digital twin, which calculates the stress distribution. So this is the basic idea. The physical device has only one sensor. The only output is the acceleration, which is integrated twice to capture the displacements. Then the digital twins has an unlimited number of virtual sensors that are free of charge. And that's the basic idea with digital inspection and monitoring. A digital twin can be instrumented easily, and the sensors are free of charge. So what is the state of art in digital twin applications for structural monitoring? Well, we have spent 1 year studying reports from Siemens, General Electric, PTC, ANSYS, and Hexagon, and MSC that are the market leaders. And we haven't found scientific publications or industrial use of digital twins yet. That's why we last year, funded by SAP and Fedem, initiate a master thesis in order to benchmark digital twins. And those benchmarks will be presented here, and they reveal a lot of research questions that we will address in the PhD studies. The first benchmark is the Stavo Bridge. This bridge was built by the Germans 74 years ago, and Vegvesenet doesn't know the structural state of this bridge. And in fact, VG has identified that the structural state of the bridges in Norway are in general bad, and as well. That's why Vegvesenet wanted MTP and Fedem to come up with a method for digital inspection. And the first thing we did was to initiate a master study, and the student has modeled the bridge and performed model analysis to see where we should put the sensors in order to capture the vibrations, which is in general a very demanding case, and that's why we have addressed one PhD for this topic. We have also seen that in order to capture the loads, we need inverse methods that, based on sensor outputs, are able to capture the loads passing through the bridge. And as you know, Vegvesenet has put restrictions on this bridge, so only one truck is allowed to pass simultaneously. And that's why we now will also rent ASCO trucks, 40-ton trucks, to load the bridge as critical as possible. And we have already monitored the bridge with physical sensors. The core team here will be Anders Rønquist from the KT department, Bjørn Haugen and me from MTP. The second benchmark is the LERKENDAL arena. That means the arena where Kjernen, the RBK supporters, are standing. And for those who attended the match between Ajax and RBK, where RBK qualified for the European tournament, You probably noticed that Kjernen was jumping up and down and caused really large vibrations on this arena. And if you listen very well, you can hear the drummer. He beats the drums with a frequency of 2 Hertz. And then this eigenfrequency or eigenmode will be initiated or start to vibrate. Not at 2 Hertz, but it's an overharmonic due to the instant jumping. And then they initiate vibrations at 8 Hertz. And then you can see the monitors, which are connected to cantilever beams under this arena. They start to shake really hard. And you know, below here, you got the VIPs from DNB, the financial guys, and they easily get scared, as you know. So they wanted LERKENDAL to study if it was safe to stand here. And we then offered a digital twin solution. So we are now instrumenting the arena, the beams here, with accelerometers. And then we have the next problem, because if you integrate accelerometer data, you will find out that after one match, LERKENDAL is supposed to be located 100 meters below ground, simply because you got drifting and sensor noise, which is being accumulated when you integrate the sensor outputs. So this is a really difficult issue. And that's why we put together with this team with Anton, Markus, Dietmar and me. And Anton, Markus and Dietmar is from the mathematical science department, and they will look at sensor outputs and other mathematical techniques in order to filter out these problems. The next benchmark is windmills. These need maintenance, and it's typically a challenging task to do physical inspection on these devices, especially when we talk about offshore windmills, which is really the expertise of Amir. Here you can see that these windmills, they transfer loads from the blades, so we need inverse methods to capture the applied loads, and also methods in order to accurately predict the stresses on these. And there are other issues related to wear of these bearings, the slewing bearing especially, and also the gear units, which usually break on these windmills at harsh weather conditions. So we have already monitored windmills in Fosen and Finnmark, and we continuously receive data for this. And that's why we also in one PhD address the issue of capturing and passing and filtering huge amounts of data. We need formats which can easily treat those amounts of data, and we need methods in order to capture when the critical loads occur, so we don't have to store all data 24/7. We just want to capture data when critical loads happens, and then we want to do the analysis, because these type of analysis can't be run real time. So the team here is Amir and Anders Rønquist, which is an expert on wear and fatigue, and Dietmar for all other mathematical issues related to this, and me and also Bjørn Haugen will be a part of this. The fourth benchmark is cranes, and cranes are really good candidates for digital inspection. They are expensive and they are suffering from wear and overload. If you look at the offshore cranes, a typical situation is that large cranes are located on small boats. And then sometimes when you have really heavy loads, this might cause instability. And then you need a digital twin to predict what happens when really critical loads are acting. You don't want the boat to roll around. You also want to study wear and the safety against the buckling and other failure modes. With harbor cranes, you want the performance to be optimal, and then they can easily get overloaded if you're not having a digital inspection tool. In this example, pretty much all technologies that we have been talking about, inverse methods, sensor technology, is of importance, and that's why we have put together this team from different departments: Bjørn, Dietmar, Antoine, and me, and pretty much everyone will be involved in this activity. The fifth benchmark is not an industrial use case. It's actually an exam written by Torger Velo, and this is a simple suspension system. And that is brilliant for benchmarking methods and tools developed by the PhD students. And it's also fit the purpose of giving live demonstrations. So if you like to see this one in practice, you can come to Perleporten. It can be used in both teaching and research. And here, the team working with this one will pretty much be Markus, Dietmar, and me. But everyone else that wants to use it in his research can use it as a demo or benchmark case. The sixth benchmark is a manufacturing cell. The original plan was to use a benchmark or an industrial cell from Volkswagen, a cell manufacturing front suspension for the new Golf. But due to confidentiality, we couldn't use it. So instead, we will use a manufacturing cell that will be built for NAPIC and Manulab, where Olav Egeland will be in charge. And here we want to apply or model a digital twin in order to capture the reasons why the final tolerances are out of range. What is the reason? Is the structural flexibility of the robots? Is it varying material properties of the goods? Is it different geometries or shapes? So the digital twin is going to monitor a product through the whole process and identify the problems that may cause tolerance issues and bad quality. This is really an exciting industrial case. And the team here will be Per Schjølberg, Antoine, Harald, and Olav Egeland, and me. These benchmarks have identified many research questions that couldn't be solved by the master students. We need PhD studies to address these. The first and most serious one is we need inverse methods for load identification. It's quite easy if you have a cantilever beam, then you have analytical formulas. But as soon as you start to look at different products like this, tower, which is initially used in a PhD by Olav Egeland and Bjarne Foss many years ago, this one is now used in order to capture the applied loads and direction here based on sensors at the bottom of the tower. So we need PhDs to address these issues, at least one. Physical sensors are expensive while virtual sensors are free of charge. That's why we need to find a method to identify an optimal distribution of sensor to capture the loads. So this research question is really related to the first one as well. But we want to put a separate PhD on this. We want, I think, to use methods from the aerospace industry back in the 90s, where you used observability in order to identify the optimal distribution of sensors. And this distribution should identify the different vibration modes, and you should also be able to separate them from each other so that you can easily identify the load. This is a real challenge. The next research question is sensor drifting and noise. We want to capture wear on a structure, for example, wear on a manufacturing cell, or wear on the drive lines, or wear in a windmill bearing. And we also want to capture drift. We want to eliminate the G gravity from measurements in the gravity direction. Typically, that's an issue when we monitor structures like LERKENDAL. Then you will see that the accelerometers give you an output in the set direction that appear to be 1G plus minus. And there are lots of noise, so when you want to use accelerometers to capture the displacements, we need to calibrate them. And we need mathematical methods to eliminate sensor noise and drifting. And also we need mathematical methods to identify the trends, the wear of structures. Predictive maintenance could be based on fatigue analysis, but on a real structure like this offshore ship or any crane or structure, there are different failure modes. You need to do risk analysis. What is the safety against buckling, collapse, fatigue, cracking, and lots of other things. And this should be covered by a separate PhD, especially because this is really important for most expensive offshore equipment and structures and bridges. The link between the physical asset and the digital model is also a critical issue. First, we need a safe way to transfer the data from the physical sensors to the digital twin. Then we need nodes in order to initiate analysis when critical loads or situations are acting on the physical asset. We need a trigger method for that. We also need a way to store huge amounts of data, perhaps also to reduce them. And we also need a cloud-based network in order to connect the processes together. Because we will not use only one digital model, it will be a hierarchy of digital models. Some are based on mathematics, some are based on physics, finite element models, and so on. And we need a cloud-based framework to operate all this. And as we all know, the devil is in the details. Sometimes you got physical assets which are really hard to model in a digital world. It might be that we can use 3D CAD, FEM models. We can do rigid body dynamics, kinematics, and control models. And we can use analytics in order to represent the digital twin. We guess that we also have to do some basic research on modeling things like cable and pulleys and the contacts and wear and so on. We probably need to do some basic research in this field. So the question is, why support this application? Well, first, the aim of this application is to address the most critical research challenges in digital twins for structural monitoring and predictive maintenance. These research topics are based on live digital twin benchmarks performed by NTNU researchers and master students. The IoT market leader, SAP, has selected by their acquisition of Fedem, NTNU and Fedem to be their main digital twin research partner. And they want to establish a next-gen lab at MTP. The listed professors, that will be the supervisors, are experts on the most critical digital twins research tasks. The research results will be state-of-art and published by NTNU, as well as disseminated by SAP and Fedem Technology. Thanks for watching.